And welcome to our official start of data structures for today. I'm going to share my screen now, and we'll go over, I'm going to give us a quick update on the schedule and what to expect for the rest of the semester. But actually, before I do this, I realize that there are a number of GitHub issues and I think emails that people have sent to me that I haven't had a chance to respond to yet. And I apologize about that. I'm just behind on all that sort of stuff now that I have the baby to take care of. So I'm hoping that today I will get caught up on all of that. But in general, I'll probably be less responsive over the weekends to those sorts of things. And so you might have to wait until Mondays to get responses from me on that. But for our schedule, what to expect for the rest of this semester. Today we're going to, and over the next 3 weeks, we're going to be talking about a concept called trees in data structures. And trees are going to turn out to be like the most important concept of this class. And they're also going to be what most students will find to be the hardest concept of this class. So each one of these next 3 programming assignments, because they are important, they'll be worth a little bit more points than the previous ones. They'll be worth either 20 or 25 points each. And because most students find them harder, you should expect that you will find them harder as well, and make sure that you allocate yourself enough time to work on them. Each one of these sort of topics, I guess, is going to introduce a lot of really like new concepts. They're going to be, in some sense, really simple concepts in that it's possible to explain what they are in just like one sentence, but they're the concepts like chess, that you can explain the rules really quickly, but actually understanding the significance of those rules and what they entail, how to play a good chess game, that's the really complicated part. And so we will talk about those things in class. We'll talk about the significance of all these things, but you should expect that it's not uncommon for students to find that their brain breaks several times while we're talking about these concepts. After we talk about these 3 concepts over the next 3 weeks, I guess I've intentionally tried to schedule these so that it's not quite at the end of the semester, so that this will be sort of like the peak difficulty week in this course. And hopefully, my hope is that that's not corresponding to the peak difficulty week in most of your other courses. That's not really like midterms or finals times in your other courses. And so that these last 2 topics here, I mean, they're not going to be trivial topics. You'll still have work to do, but you should find them significantly easier than these topics. And our last topic is also going to be hopefully a really fun topic that you'll be implementing an AI based on all of the data structures that we've used so far for the game of Risk. We will also have a final in this course, and the structure of the final, what it's going to be like, is you'll have, I'll give you the final at the beginning of finals week, and you'll have all of finals week to complete it. So it's not just going to be like a 1 hour, 2 hour kind of timed thing. You'll have as much time as you need, and so hopefully it won't be a high stress sort of endeavor. And really the main, I guess, most stress you'll find is the next 3 weeks. Any questions about anything administrative like that, about what's coming up in our course? Okay, then we will get started. So week 10, talking about binary search trees, and this is a particular example of recursive data structures. And I've mentioned a couple times now that there's this binary search tree special data structure that is sort of the foundation of Google and these large scale search engines. And so we'll be starting talking about this week about that concept this week and finishing that up as we talk about all these trees. And so I have this as our comic this week because you should expect that the code that you'll have to write this week is going to be particularly subtle and difficult compared to previous weeks. A lot of students I have found in the past find recursive functions particularly difficult to work with, and you're going to be implementing a lot of recursive functions over the next few weeks. Probably on the order of 20 or 30 different recursive functions, each one's doing very different things. Okay, so our motivation. So binary search, so the algorithm that we talked about before spring break, that lets us check whether something is in a sorted list in logarithmic time. And so that's great. The difficulty of that was, though, that we had to sort things, and adding new elements to a sorted list takes linear time. So for large scale data, like the internet, you're building an index of the web like Google does, that doesn't work. Binary search trees are fixed to this. They let us perform both the insertion and deletion and the lookup in logarithmic time. And so the right way to think about them, the sort of motivation that you should have in the back of your mind as we go through our lectures, is to think of them as a combination of doing both the sorting step and the binary search, like searching step, in a single thing. And so because we're doing both of them together at once, that's why we're getting this logarithmic time. We'll see later on that you can actually use binary search trees and all the variants that we'll discuss as sorting algorithms. So you can use these as an alternative to, say, quick sort or merge sort to do your sorting. This week, we're going to talk about the simplest possible version of these binary trees, the binary search tree. And we'll see that we'll see the motivation for why in a lot of cases it's going to have login time as its runtimes. But we'll also see that in the worst case, it's not actually login, it's going to be linear time in the worst case. And so these modifications, these alternative trees that we'll be exploring, those are for guaranteeing they'll build off of the BST. They are sort of special types of the BST, and they are going to guarantee that we get this login time. The only real downside of a BST is that their implementations get a lot more complicated than these the implementations that we did before spring break of sorting and searching. But fortunately, once you've done it once, you'll never have to implement these things again. You'll just be able to use other people's versions of these. So reference in the textbook, these sections right here, I think the textbook does a decent job about explaining these concepts, so it's a good reference. And there's also lots of code in the textbook. So in class, we're gonna really be focusing on sort of the high level big picture concepts, occasionally talking about code, but not as much code as we've been doing up till this point, really focusing on the high level big picture concepts. And so I recommend looking at the textbook if you want more like specific code examples of doing these algorithms. I mentioned that binary search trees are an example of a recursive data structure, and in a lot of data structures classes, they would cover these three other recursive data structures before talking about binary search trees. These are really important for computer science specific classes, especially classes that are not taught in Python. So it's very common, say like at Mud and Pomona, for the classes to be taught in a language like C++. And in those classes, they would definitely talk about each of these recursive data structures here before talking about binary trees. In Python, however, these linked lists, they just don't get used in Python. Yeah, the deck turns out to be an example of what's called a doubly linked list, and that's implemented in C, and Python just interfaces to C, so you have access to that. And there's never a situation where you want to actually implement it in Python. So we're not going to go over that. If you are curious about those data structures, and they are important if you're, say, trying to do a software engineering job somewhere. They're the sort of things that you might get asked in an interview. I just have 3 links right here, videos that go over them in pretty good detail. So you're welcome to look at those, but not required. And the textbook also does a good job about those. And then this week, we're going to cover binary trees, and then the specific example of binary search trees. And then in subsequent weeks, we'll see these other binary trees. Any questions about any of that before we actually get started on the material? Okay, so I'm going to switch our screen over, not to code yet, but to this window here where we can draw out some data structures. And I'm going to draw out some examples of trees. I'm going to go over a whole bunch of definitions, talk about some really some of the basic algorithms just from the conceptual level. And then after we do this, then we'll start taking a look at code for a little bit. So a tree in computer science is typically drawn where there's a bunch of circles, like this, and edges or branches connect the circles. Inside of the circles, it's customary to write the values that are contained in the circles. And those values can be any type at all. I'll be using integers for most of the examples. So I'll have something like a 5 here, a 10 here, a 1 here, and a 3 here. And the numbers, or whatever I write inside of the circle, we call the value of that particular node. So 5 is the value. This circle here is the node. And this line here is the edge or branch. In computer science, it is customary for us to draw our trees upside down. So up here at the top, we would call, let's see, I'm gonna make this tree a little bit bigger before doing that. And when I leave a node empty, it means there's something there, but we don't really care what's in there. So at the top, this is what we would call the root of the tree. So every circle is a node, but the very topmost node is the root. And all of these bottom nodes we call leaves. So that's a leaf, 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 and that's a leaf. These are leaves. And so the metaphor is that, like, again, it's upside down, but this is where the ground is. This is where our tree is rooted to the ground, and then these are all the branches coming out. And then if you have something that there's no more branches coming off, it must be a leaf. We also, it's customary in computer science when we're talking about trees, we use a lot of family language. So if we're looking at this node right here, I'm going to draw it in red, or circle it in red. Then we would call this node up here the parent. This node right here the child. This node right here the sibling. And all of the nodes above it. So everything up here, these are the ancestor nodes. And then everything down below, the descendant nodes. And so all of these in particular would be descendant nodes, but the descendants of our siblings, they're not descendants. We could, sometimes you'll get people talking about up to like aunts and uncles and cousins and first cousin once removed in the tree, but typically we don't go into that much detail. And if you just talk about parents and children and siblings and ancestors and descendants. This particular tree is an example of a binary tree. It's a binary tree. Because every node has at most 2 children. So in a binary tree, every node is allowed to have 0, 1, or 2 children. If it has 0 children, then it must be a leaf. If it has 1 child or 2 children, then we would call those internal nodes. So everything that's not a leaf is also sometimes called an internal node. Here, it looks like I ended up drawing everything so it either has 0 or 2 children, but we could also add on another node, say right here. And now this one here is the leaf. And this one's not a leaf, and that's perfectly okay. This one only has 1 child. When we're specifically in the case of a binary tree, it's also customary to talk about the left and the right children of a particular node. And so this 3 right here would be the left child of 1. This 3 right here would be the right child of 1. The 1 is the left child of 5. The 10 is the right child of 5. This 3 has a left child, but it has no right child. Other important definitions are the height of a tree. The height of a tree is the total number of, if you start at the root, the total number of edges that you have to travel to get to a leaf. So in this case, the height would be equal to 3. And there are some paths going from the root to a node. So here we only have a length 2 path going from the parent to this particular leaf node right here. And so this node we would say is at height 2 or at level 2. This is level 3, level 2, level 1, level 0. And but just because we have some leaves at height 2, that the height is still 3 because the maximum level that a leaf is at is 3. Any questions about any of these definitions so far?
Mike, so 3 is a child, like the 3 on the left is a child, but the 3 on the right is not a child?
We'd say the 3 on the left right here is the left child of 1, and the 3 on the right over here is the right child of 1. So it's perfectly okay to have the same number appear in multiple values for multiple nodes. It's also, but you just have to be clear in that case which one you're talking about. So they're both children. It's just this one's the left child, this one's the right child.
Okay, so, and 1 is the child of 5, right?
Correct, yeah.
Okay, and could you also explain why there's at most 2 children?
So yeah, this is a good question. The question is, why is there at most 2 children? And we haven't talked at all about a why to any of these yet. This is all just purely definitional. And for a binary tree, it's just the definition. Binary means 2. And so if a tree has 2 children, at most 2 children per node, we can call it a binary tree. There are many other non-binary trees. So if we came down here and had a tree that looked like this with, say, now this tree has 4 children under the 5. Maybe we have more children on some of these. We would say this is a non-binary tree. It turns out that in many situations, binary trees are going to be easier to work with. We talked a little bit about with binary search that there's this alternative algorithm called Trinary Search where you split into 3 instead of into 2, and that binary search actually has the better asymptotic runtime. And a similar phenomenon will occur with these non-binary trees. that it's possible to do these non-binary trees. We might even talk a little bit about some situations where you might want the non-binary trees, but in general, binary trees are going to be both easier to code and give you the better runtimes. So 99% of the time, if people are talking about trees in computer science, they're talking about these binary trees. Good question so far. If you do have questions, it's important to make sure that you get these clarified now, because I'll continue to use all of these terms and just sort of assuming that you have sort of an intuitive grasp about what they mean. I'm never going to ask you, say on the final, give a formal definition of a child, or given this node, list all the children. Instead, the way this knowledge will come up in this class is we're just going to be using these terms all the time, and you have to be comfortable with understanding what we're talking about.
Mike,
sorry, go ahead.
One more question. So 1, node 1 and 10, they're not leaves?
Correct. 1 and 10 are not leaves. So a formal definition of a leaf, we'll write out a formal definition. A leaf is any node with 0 children. And so using that definition, coming up here, looking at 1 and 10, we can see that both 1 and 10 have children, and so they can't be leaves. Here, even this 3 here, it has a child. It also has this sort of right-hand side that doesn't have any children, but because it has a child, it's not a leaf. Here, this one, though, has no children, so that's why it's a leaf. Good questions. Varun, did you have a question?
Yeah, I was just going to ask what the difference is between a leaf and an edge, but it seems like an edge has a child.
So an edge is one of these lines in particular. An edge is a connection between 2 nodes. And a leaf is, in particular, a node. The standard, so when we look at code in a little bit, these edges are not going to be anywhere explicitly represented. What we're going to have is we're going to have a class with each class representing a node, and then there's going to be no variable or anything that's explicitly representing these leaves. We'll just have a, well, let's go ahead and take a look at the code to clarify this. So here, this is a binary tree.py file. This is going to be the base of your homework assignment. You'll have to complete some functions inside of this file. And you can see that there's this node class right here. And this node class is going to represent each one of those circles. Each one of these nodes is contained in, is represented by this class. Every one of these nodes will have 3 attributes that it cares about. The value attribute. So that's the thing that I've been writing as the thing inside of the node. And I'm going to continue using integers when I write them out, but they could be strings or integers, floating point numbers. There's sort of no restriction on what they can be, as long as the entire tree uses the same type. And then there's this self.left and self.right. And I have this note here that the left should always be a node and the right should always be a node. If the left is a node, then we have an edge between self and left. So if right here, self is 1, then self.left would be a node whose value is 3, and self.right would be a node whose value is 3. If self was 10, this would be self.left, this would be self.right. In this case, when we have, if we have a leaf where there's no connection to other nodes, then self.left and self.right would be equal to none. So I'll write that out. For a leaf node, self.left and self.right are both none. And so you can see in our constructor, by default, it's going to create a node that's a leaf node because it's by default passing in none for left and right. All great questions so far. Any other questions? Okay, we have a few more definitions to go over, and then we'll talk about the some of the interesting algorithms. Sam, go ahead.
Yeah, so what are some of the applications of these binary tree structured programs? Like when would you want to use this? When would you want to use this sort of structured code?
Yeah, good question. So the main application that we're going to be looking at is for searching. That we'll see that this binary tree, in particular a binary search tree, which is a special type of binary tree, is going to let us do the searches in logarithmic time, but still being able to do the inserts and updates and deletes also in logarithmic time. So the way to think about this binary search tree is like the binary search algorithm that we covered a couple weeks ago, but even more powerful, because not only can we do the find fast, we can do inserting, searching, everything fast. So this is like where every time in Google you type in your query, it's a binary tree that's in the background that's going to be making it fast under the hood. It's a great question, great thing to be like keeping in the back of your mind, but that'll become more clear as we start seeing more examples and actually see the algorithms that operate on it.
Hey, Mike.
Go ahead, Jonathan.
So based on how I understand the node class is written now, does that mean that we're going to have to be building these trees from like the bottom up, or like from leaf to root, since it sounds like they'll already need to have their left and right attributes, is it defined?
That's a great question. So this is a good time for us to talk about how you can actually create these in code, and we'll talk about how to visualize them in code as well, which is going to be really important for debugging. So I'm going to switch over here, and we'll take a little bit more detailed look about this node class. And you'll see that there are only two functions inside of it. There is this init function and this string function. And if we come down here, then there's this binary tree class, and this is sort of the main class that contains a lot of that you're actually going to have to work with. You're not going to have to modify the node class at all. You're just going to have to modify the binary tree class. And inside of this is where you'll be working with these node classes. The binary tree class, the only thing that it has inside of it, the only variable is a link to the root node of the tree. If the tree has nothing in it, then the root is none. If the tree does have something, then it has a node. And then we would get access to the children by sort of going down this node. The question was specifically about creating these binary trees and what does that look like? And there's an example of that in the test file for the binary tree class. So I'm going to press GT on my Vim window to switch windows over here to look at the binary tree. And actually first, you'll see that there's no numbers on the left-hand side over here. What I'm going to be doing next is copying and pasting some code from here down into a Python window down below here. And I turned off the numbers so that I can actually do this copying and pasting. You notice that if I select like this, it's going to bring in all of these numbers, which would mess things up. So in order to temporarily turn off line numbering in Vim, it's :set no number. It's just a useful thing that that I do when I'm trying to copy and paste to help my debugging with Vim. Each one of these examples is in a binary tree that's been constructed manually for you. And so all of the test cases that you'll have to run, they'll have to be able to run on these 4 examples, example 0, 1, 2, and 3. And what we're going to do next is I'm going to copy these code snippets down from up here into Python down below. We'll see how you can work with these trees a little bit, how you can go from one node to the next, and we'll see how to draw them out based on these structures. So down here, I'm in my containers folder in the BST branch, and if I were to type ls and ls containers like this, you can see that there's two new files up here, binary tree and bst.py. The binary tree one's the one that we are most interested in right now, and I'll open it up by python 3-i containers / binary tree.py. I'm going to take, before I hit enter here, I'm going to pause and just emphasize that notice that nowhere did I use the cd command, that I'm staying in the root folder of my repository and calling these files from the root folder by actually specifying the full relative path to that location. This is going to be really important when you're debugging to make sure that you don't use the cd command basically ever. You cd into the repository and then you stay in the root of the repository. And then anytime you're trying to access a file, you access it with the relative path like this. I've noticed while working with a number of you on the Twitter assignment especially, but a lot of the other ones, a lot of you are still into the habit of cding into a folder and then so it's doing something like cd into containers and then Python 3 binary tree.py instead of staying where you are and writing out the full path. If you do that, you will get lots of very difficult to explain bugs. So you really need to get into the habit of not using the cd command at all. Okay, so do this, and I've loaded up my binary tree.py file. And you can, let's see that I have access to binary tree like this. It just outputs the class like so. And if I were to copy and paste one of these example segments down below here like this, I've created this underscore example1 binary tree. And so if you just try to display it like this, you can see there is no repr function for this node value right here for this binary tree. And the reason for that is because there's no just easy one-line command that you can call that will recreate this binary tree exactly as it is. Recall that the underscore repr function, or the dunder repr, or the magic repr function, the purpose of it is to give you a one-line command that can recreate the object. But there is still a visualization command that we can use to visualize this tree, and that's the str command. That this binary tree, come up here, come back up to the binary tree or the node class. You can see that it implements this str function, but does not implement the repr function. And so that's why when we do str, we get something like this. But when we do this, which implicitly calls the repr function, we get this ugly looking thing here. And so the next thing that we're going to do is we're going to talk about how does this string right here represent a tree? How can we go from this string to drawing the tree that corresponds to this string? And this is going to be really important because as you're implementing all these algorithms on binary trees, in order to debug it, you're going to have to print out what the binary tree is. When you do that, you're going to get a string that looks like this. And you have to be able to really easily just look at this and understand, is that the tree that you want, or is that a different tree? Is there a bug in your code? So let's talk about how do you actually draw this picture right here. In order to do that, I'm gonna real quick do some fiddling with my screen. I'm gonna send this window right here, this terminal, to the other screen. So I have it side by side with my drawing area. Scroll down to a blank section so that we can draw this, this string right here. The first thing that you'll notice is that there's a bunch of parentheses in here, and the parentheses map contain a single node. So here, this 4 is a single node, this 5 is a single node, and this 3 is a single node. So the parentheses are supposed to remind you of like there's a circle around this 4. And so the first thing I'm going to do while I'm drawing this is draw a 4 and a 5 and a 3 with circles around them. Oops. A 4 and a 5 and a 3, all with circles around them. And that corresponds to this 4, this 5, and this 3 right here. Now that I've done this 4 and this 5, I'm going to get this 2 right here. And you can see that this 4 and this 5 are inside of the parentheses for this 2. This 4 is on the left and this 5 is on the right. So this 4 corresponds to the left child of 2, and this 5 corresponds to the right child of 2. So I'll draw 2 right here with 4 as the left child. Whoops. There we go. And 5 as the right child. And that takes care of this whole thing right here. The last one here is this 1, and this 1 is going to be our root. Whenever you have the outermost parentheses, that corresponds to your root node of your tree. And so we'll draw the 1 up here. And this set of parentheses right here and this set of parentheses right here are both contained inside of the parentheses for the 1. So those are our 2 children for this 1 tree. So the 1 will come like this, and then down like this to the 3. You'll notice that I've drawn this, I know this tree is kind of a little wobbly, that I could have also drawn this tree as 1, 2, with the 3 sort of obviously on the same level as the 2, like this. And these 2 trees are, or these 2 diagrams are meant to represent the same exact tree, how it's being stored inside of the computer. And so if it's easier for you to visualize after drawing this tree like this, to redraw it like this, feel free to do so. But you can also keep it like this, or after you get the hang of doing this a little bit, you can, you'll start to be able to just look at this and get a sense for whether it's correct or not. The real difficulty here is there's just so many parentheses, it's really easy to get lost in your parentheses and remember which parentheses does this one match up to, and be really careful about making sure that you line them up correctly. Are there any questions about how I went from this string right here to these diagrams over here? Okay, I'm gonna move this window back over to the other spot, and there we go. It's down on the bottom, same setup that we had before, but now I'm going to, let's take a look at our test cases for the binary tree.py again, and we'll see that this right here, this is the code that I used in order to create this string right here. So now I'm going to take this code, this top window, and move the top window back over to that drawing area. And now what we're going to do, so this is the example 1 right here. This is the tree structure that I used to draw out these trees right here. And we'll see that this root node, node 1 at the root. And then if we look at root.left, we'll get this node 2. So here's our root, go to the left, there's our node 2. If root.left, so starting at the root, going to the left again, that's our node 4, and then root.left.right, so root.left.right equals 5, and root.right equals node 3. So root1.right node 3. So at this point, this is our only sort of method for constructing these trees, is to manually go through and set the left and the right values kind of mechanically. And so that's what this is doing right here. This actually created these values over here, or these diagrams over here, these trees over here. Are there any questions about how this corresponds to these trees?
I have a nomenclature question.
Mhm.
I understand why we use the node like class to like place these integers in.
Mhm.
But is is every leaf a node?
That's correct. Every leaf is a node, but not every node is a leaf. So a leaf is just a special type of node, just like the root is a special type of node. We don't have separate classes to represent the leaf and the root. We don't have special classes for sibling nodes or parent nodes or children nodes. It's just when a node satisfies certain extra properties, we give it one of those extra names as well. It's a great question.
Mike, do we fill the left child or the right child first?
Great question. So the question is, say, on these two lines right here, I'm doing the left first and then the right. And is that required? Or could you say, do something like this, doing the right first and then the left? And the answer is it doesn't matter that you can do left first, right first, either way. Move this up here, say like that. Doesn't matter. We could move this right in the middle like this. All of those are going to be valid things to do. The one thing that you do have to be careful with is, so here, this left node right here is a child of this left node right here. And so in order to do this line right here, because this references this, you must create the parent before you create the child. The order of the siblings doesn't matter, but you must create a parent before you create a child. And so it makes sense the same way with people. You can't have a child person who doesn't have a parent yet. So if I were to say, move this one up here, this will generate an actual error and would not work. Let's see, to demonstrate what that error message is going to look like, I will move this screen again over here. So I'm back in my, we have the same window we had open on the top now, and then on the bottom is that same Python window. I'm going to quit out of Python down here, press Control D, press the up arrow to restart Python. And notice that this is the binary tree.py file that I opened up, but this is the test binary tree up here. So it's different files that we're looking at. And down here, I'm going to copy and paste these 3 lines. Let's actually start with these 2 lines right down here. You'll see that there's no error message yet. But if I do this line right here, so recall that the problem with this line is that this left is a child of this parent, but this parent is created right here. So this parent doesn't exist yet. And we'll see what sort of error message we get. You'll get this none type object has no attribute left. Anytime you get an error message that looks like this, it means that somehow you are accessing the child of a parent that doesn't exist. So anytime you get something that looks like none type object has no attribute left or no attribute right, that's what's going on. To fix that, you always have to first create the parent and then create the children. All great questions so far. Any other questions at this point? Okay, so what we're gonna do now is there's 3 algorithms that we need to talk about on binary trees before we can talk about binary search trees. So binary search trees are a special type of binary tree that have this great property of the logarithmic runtimes. But before talking about those, we still have to talk a little bit more about binary trees in general. I'm going to switch back over to the notes here. And there's these 3 algorithms are traversals, the height algorithm, and the size algorithm. So the traversals are the, I think conceptually the kind of hardest to understand. So that's what we're going to spend the most time on. And I have a code in your homework assignment that sort of pre-does these a little bit for you. The height and the size, I think, are conceptually more easy. It's obvious why you might care about the height and the size of a tree. And so those you'll have to implement from scratch. A lot of the techniques about recursion, though, that we talk about with these traversals are going to be applicable into how you would want to implement these. So traversals. Switch back here and come to our binary tree. And I'm going to scroll down a little bit more into some of the functions that exist in this binary tree class. And the first one of these that's interesting is this print tree. And this print tree function does these traversal algorithms. There's 3 traversal algorithms: the pre-order algorithm, the in-order algorithm, and the post-order algorithm. And so this print tree method, all it does is gives you sort of a one function interface to select which one of these 3 algorithms we're going to do. And then there's separate functions down here that actually do those algorithms. So here they are. This does the pre-order, and then the in-order and the post-order. And you can see that I have these already are already completed for you. So you don't have to modify these in any way. Let's see. So the next thing we're going to do is we're going to run these algorithms to see what happens. And in order to do this, down below, I'm going to re-quit out of Python, restart Python, come over here, re-copy and paste this binary tree class down here. So I have this, this tree for us to work with and call these functions on. So you can see that I'm doing a lot of this copying and pasting of these examples down into Python down here. And this is sort of the standard way that I go about debugging these, my code when I'm working on problems like this. Okay, so we have example 1, and I want to call the print tree function on example 1. So it's underscore example1 dot print tree. I've talked a little bit about tab completion before in the bash shell. I don't know if I've talked about it in Python, but you can see tab completion actually works inside interactive Python. I have print underscore typed out right now. There's only one function that satisfies this this pattern at this point, and if I press tab, it completes that function for me. So I do that a lot while I'm typing, especially on these class methods, because they can get very long. And so print tree, it takes 2 parameters, but recall that this self parameter gets passed for us automatically, so it's only this traversal type parameter that we actually need to think about. And there are 3 traversal types: pre-order, in-order, and post-order. And so let's pass in the pre-order string and see what comes out. You'll see that we get out a string like this that has just the numbers inside of the tree. Each one of these nodes up here will get displayed exactly once down here. But you also see, and in this case, the pre-order traversal is going to give us the numbers in the same exact format that the string function gave us the numbers in. Turns out that internally this string function is implementing a pre-order traversal in order to draw this diagram like this. Now let's just see what the in-order traversal does. And you can see that we still get these 5 numbers down here. They're just in a different order. And then the post-order traversal also gives us those numbers. They're just in a different order. So now what I want us to do is think about, what are those orders? Why did we get these particular combinations of numbers? So in effect, what is the meaning of a pre-order, in-order, and post-order traversal? I'm going to once again switch my screen so that the code that we have right here, we can see it side by side with the drawings that we have of these trees. So this tree again is the example 1 tree. It has the 1, 2, 3, 4, 5 numbers, 1, 2, 3, 4, 5 that appear down here. And I'll walk through sort of by hand what a pre-order traversal does, and then we'll see how it corresponds to these numbers over here. So in a pre-order traversal, you first visit the node you're at, then visit the left child, then visit the right child. And this is just the sequence of things that you should remember for what a pre-order traversal is. And so when we start at the root, so starting right here, this is going to be the first location that we go to at the root. You first visit your node, and then we visit the left. So we come down here, and this is position number 2. When we visit the left, that's going to be a recursive call. So we'll visit this one, and then, so we're at this position right here, visit the node, visit the left. So that comes down over here. This is position number 3. We recall our pre-order traversal on this, visit the node, we get the 4, visit the left, well there is no left, visit the right, well there is no right, so we're done visiting this node, and we can come back up to this node. At this point, with node number 2, we've visited the node, visited the left, but we still have to visit the right. So we come down here, and 5 is the 4th position that we go to. After we visit the 5, we visit the left, there is no left, visit the right, there is no right, so we come back up to the 2. Once we've come back up to the 2, we've visited the node, visited the left, and visited the right of the 2. So we're all done with the 2, and we come back up to the 1. When we're at the 1 right here, well, we've already visited the node, visited the 1, we have visited the left, we've gone down over here, so all that's left is to visit the right, and we go down this way. And so this is the 5th node that we go to in our pre-order traversal. If you see all of these red numbers right here, these are the order that we visited each of these nodes in. And so they correspond to the locations that we printed out the numbers over here. We first did a 1, 2, 4, 5, 3. 1, 2, 4, 5, 3. And that's why these numbers get printed in our pre-order traversal printing. I did that pretty quick. So does anybody have questions about what happened while I was doing that? Okay. If you do feel a little bit fuzzy about that, that's okay. We'll take a look at the code here in a minute, and that will be another way to help clarify that, hopefully. We're also going to take a look at our next traversal type, the in-order traversal. Now, and this might help explain when we see the difference between these, see what's going on. So the in-order, I'll do an orange. So here, we first visit left, then visit the node. Let's move this over just a little bit. And then the last thing we do is visit the right. So when we do an in-order traversal of this tree right here, I'll do it on the same tree, but the red corresponds to the pre-order and the orange will correspond to the in-order. When we start at the root, the first thing that we do is visit the left this time. So we go down here to the 2. Now when we visit the 2, the first thing is we visit the left. So we come down here to the 4. The 4 now gets our 1. When we're at this 4, there is no left, there is no right, so there's nothing to do here. Come back up to the 2. At this 2, we visited the left, so now it's time to visit the node. So that gets position 2. And now the next thing is we visit the right. So we go down here. At the 5, we visit the left, there is no left, so we next visit the node. This is the third node that we visited. And then we visit the right. There is no right, so we're done here, coming back up to the 2. In the 2, we've already gone to the left, already visited ourselves, and already gone to the right. So we've done all 3 of these steps, so we come back to the 1. In the 1, we have already gone to the visit the left, finished all the left subtree, and now we're visiting the node, visiting this node right here. So this is a 4, the 4th node that we visited. And the last step is that we visit the right. So down here, go to the right, and when we're at 3, visit the left. There is no left, visit the node itself. So we get a 5 here, and then visit the right, and there is no right. And so if we use the orange numbers and look at them in order, we get a 4 and a 2, a 5, 1, 3. And if we come down over here, our in order traversal goes 4, 2, 5, 1, 3. So conceptually, the thing to remember about the difference between a pre-order traversal and an in-order traversal is just that the in order, we do left, then node, then right. Pre-order, we do node, then left, then right. Otherwise, the thought process and thinking recursively is kind of the same sort of thing. Are there any questions at this point about what we did for the in order or the difference between the pre-order and the in order traversals? Okay. Then the last one is a post-order traversal. And so writing that out in blue. Oops. Post-order. And so a pre-order, we visit the node first. In order, visit the node in the middle. And a post-order, we visit the node last. So be visit left, visit right, and then visit node. And I'm not gonna walk through the step-by-step, but you'd see that we get these different set of numbers down here as the order of things that we visited them in. In general, the sort of most useful of these traversals is typically the in-order traversal. This is the one that we're going to end up relying on heavily when we do the binary search tree. But we also saw that this pre-order one was kind of useful for this visualization right here. And this post-order one, it doesn't really have too much use. It's just kind of presented for symmetry reasons that, okay, you can visit the node in sort of any one of these locations at the beginning, in the middle, or the end. And all of those give you valid ways of ordering these numbers together. Okay, so I'm going to move this terminal window back with the code, and we'll take a look at the code. The code's up top and the terminal window down below. And we'll take a look at the print order right here. And if you look at these print order traversals, you'll see that for the pre-order, well, this is visiting the node. Then we have a recursive call on the left, start.left right here. And then a recursive call on the right, on 83, start.right right here. So it's pre-order because the visiting the node happens in the very beginning. If you look at the in-order traversal, you'll see that visiting the node happens in the middle, and the post-order traversal, visiting the node, happens at the end. The really important thing to take away from here is these recursive calls right here. That's what is going to make this whole thing work together. Recall that anytime that we have a recursive function, we need two things. We need a function that calls itself. So here in the post-order print, we have the function calling itself. In this case, in order for it to call itself, it needs to have this self dot because it's a method inside of a class. And so it looks a little bit different than the recursive calls that we've seen before, but it's still a recursive call. And so it still satisfies that first condition of a recursive function. The second condition that we have, though, is that it must have a base case. So in this case, or for trees, our base case is typically going to be when we're at a leaf node, or maybe in some sense you could think of that as below a leaf node. And that's what this if condition right here is trying to check for us. It says if start. And this start is going to be that when we do this recursive call on the post order print right here, passing in start.left. So start.left will get passed in right here as this start. If this start.left is none, so this node variable start contains no children or no left child, then we'll pass none. That'll be equal to none. Start will be equal to none. We'll do if none, that evaluates to false. And so nothing, none of these will get executed. We'll just do the return, and that's our base case. So we do have both a base case and a recursive call, so we satisfy all the things that we need for a recursive function. Similarly, if we, for the in order print, you can see that they all have the same formula of capturing our base case right here. For the thinking about the runtimes of these traversals, we could try to appeal to the master theorem and write out a bunch of math that way. But in this case, we can just be a little bit less formal and think about that when we're looking at these pictures, we know that we visited each of these nodes exactly once. So that means the runtime must be theta of n, that it can't be more than that because we never visit a node twice. And it can't be less than that because we never visit a node 0 times. So it's a somewhat less formal runtime justification than we were doing with the master theorem, but this is something that justification is something that any practicing computer programmer or any theoretical computer science would consider to be a legitimate proof that the runtime is theta n. Are there any questions about anything that we've talked about with the traversals? Okay. So I mentioned that I'm giving you part of the code for the traversals, but there's still a little bit more that you have to do. And down here, there is this toList function, and this is what you're going to have to implement. And the toList function is going to do either a pre-order, in-order, or post-order traversal, but instead of actually printing the value, it's going to return it as a list of the values that were in our tree. And in general, this is a good sort of programming practice that whenever you're tempted to print something out, instead of printing it, just put it in a list or put it in some sort of container, because you can always print that container if you actually want to visualize it. But once it's in a container, you can also do other operations to it to manipulate its contents using list comprehensions and maps and the filter function, all of those tools that we've seen before. And you can't do that if you're directly printing things. So that's sort of my general rule of thumb whenever I'm developing a data structure. When I'm tempted to print a value because it will help me in debugging, instead of printing, I return it as a container somehow, as a list, and still just as easy to print it and visualize it that way. But now I can also do other things as well besides printing it. Any questions about this toList function? Okay. Let's see. Ariman, did you have a question?
No, I didn't.
Okay. One thing that I'll highlight is that this toList function, you can think of it as it's kind of like an iterator because we're returning some structure that you could iterate over for the contents of this, this data structure. And if we were going to be a little bit like really picky on our memory usage, we can actually return generators instead of a list, and that would save us some memory. But it would be impossible to use the actual magic iter function on this to accomplish this. And that's because there's no one canonical way of converting a tree structure into a linear structure like a list or a generator. That we've seen here that there are 3 ways that we could do it. And if we wanted to, we could even define some other maybe weirder ways. But whenever you have an iter method, that means that you've picked there's only one way to convert something into a generator, and everybody has to use that only one way. And so that's why we're not using the iter magic method, is because we don't want to force people to only use one type of traversal. We want to give them the option to use any type of traversal that they want. Let's see, in this binary tree class, there's 2 other algorithms that you have to implement this, the length, so actually computing the number of elements in the tree, and the height, computing the height of the tree. And we'll talk about those on Wednesday, what you need to do for them. You'll see here that there's this special thing called a static method. This is called a decorator in Python, and yeah, so we'll talk a little bit about that on Wednesday, what you have to do for it. And then on Wednesday, we'll also talk about, so I'll open up the other file right here, the bst.py class. And this is so every BST is a binary tree, but not every binary tree is a BST. And this is the actual class that's going to give us those fast inserts and lookups. And we'll talk about the runtimes for this and what you have to do for that. My recommendation is that you get started on doing this, these traversals before Wednesday, because again, I think most students are going to find this is going to be the most challenging homework assignment you've had so far. And so the earlier you get started on this, and the earlier you can, or the earlier you get started, the more time you'll have to ask questions and get those resolved, so that you can move on to the harder parts of the assignment. So with that, that's the end of our class for today. I'll still be around for office hours now if anybody has more questions about what we talked about today. Or as a reminder, your Twitter assignment is due at the end of this week as well. So I'll also be available for questions about that. But otherwise, I will see you all on Wednesday.